All right, let's dive in. Today, we're talking about something that honestly feels like a true programmer superpower, taking direct control of your computer's memory. We're talking about dynamic memory allocation.
So here's the game plan. We're going to start by uncovering a really cool secret about arrays, then we'll see where they fall short, the limits they have, and that's when we'll unlock a powerful new tool to smash right through those limits. Finally, and this is super important, we'll learn the #1 rule to use this power safely and how to sidestep 2 really dangerous traps.
Okay, first things first. To really get what's going on with dynamic memory, you have to understand this one foundational secret, this hidden link between arrays and pointers.
You know, if you've ever been coding in C++, you've probably noticed this, right? Sometimes an array's name just acts like a pointer. It's a common point of confusion for sure, but the reason why is actually pretty simple.
And here it is, the big reveal. An array's name isn't really the array itself. It's just a constant pointer to the memory address where that very first element lives. So if you look at this code, we make an array called str, and then we make a pointer, ptr, that points to the first element of str. So what do you think happens when we print them both out?
And boom, there's the proof. Look at that. The output shows that our pointer, ptr, and the array name, str, are holding the exact same memory address. They are, quite literally, pointing to the very same spot in your computer's memory.
And this whole secret, it's the reason we can use those square brackets with arrays. When you write something like str of 2, it's just the convenient shortcut, what we call syntactic sugar. All it's really saying to the computer is, hey, start at the base address of str, hop forward 2 character-sized steps, and tell me what you find there. It's all just pointer math under the hood.
Okay, so arrays are basically pointers. Got it. That's a great starting point. But, and this is a big but, this normal way of making arrays where we hard code their size has a major limitation. It's a wall that every single programmer smacks into eventually.
And this slide just lays it all out perfectly. On the left, you've got static allocation. When you write int scores 100, that size is baked in when you compile your code. That memory lives on something called the stack. But what if you need flexibility? Well, for that you need dynamic allocation, which uses a whole different area of memory called the heap. Think of it like this. The stack is for all the pre-planned stuff. It's fast, it's super organized, and the computer manages it all for you automatically. The heap, on the other hand, is like this huge open warehouse of memory that your program can just walk into and request chunks from while it's running.
And that brings us right to the central problem, doesn't it? I mean, what if you need to store a list of grades, but you want to ask the teacher how many students are in the class first? A static array just can't do that. Its size is fixed. We need a way to get into that warehouse, that flexible heap.
And this is where we get our superpower. This is how we break through that wall. We're going to use one little keyword that is basically the key to unlocking all that flexible memory sitting on the heap. And that magic key is the new operator. When your program is up and running, new is your way of tapping the operating system on the shoulder and saying, hey, I need a piece of memory from the warehouse right now. And if it's available, the system hands it over and gives you back a pointer to the start of that block.
And right here, this is the light bulb moment. Look at this code. We're asking the user for a number, we store it, and then, bam, we use new to create an array of that exact size. This is totally impossible with a regular static array. We just built a custom-sized container on the fly. How cool is that?
So you've used new to check out memory from the heap's warehouse. But this comes with a huge responsibility. You know the saying, that memory on the heap is now your problem. It's not managed automatically. You have to give it back when you're done.
And the counterpart to new is delete. It's the other half of the equation. This is you telling the system, hey, I'm finished with this memory, you can have it back now. And it is so important to use the right version. Just delete for a single item and delete with the square brackets if you made an array.
This life cycle right here, you should burn this into your brain. It's the recipe for doing this safely every single time. Declare a pointer, allocate it with new, use the memory, and then, this is critical, deallocate with delete, and finally, nullify the pointer. You follow these steps, you are going to save yourself from so many headaches.
Okay, to really master this power, you gotta know the dark side. You have to know the traps. If you mess up that life cycle, you are almost guaranteed to fall into one of 2 of the most common and frustrating bugs in programming. Let's look at what they are and how to avoid them.
First up, the memory leak. The best analogy is a rental car.
Use new, and the system gives you back a pointer. That's your car key. A memory leak happens when you lose the key before you return the car. The car is still out there, taking up a parking space, but nobody, not you, not the system, can ever use it or return it for as long as your program is running.
And here's a classic way it happens. Imagine PTR2 is holding the key to memory block B. Then you just reassign PTR2 to point to block A instead. Well, what happened to the key for block B? It's just gone. You dropped it, and now block B is orphaned memory, lost forever, leaking from your program.
Okay, trap number 2 is the dangling pointer. This is basically the opposite problem. You did the right thing, you used delete, and you return the rental car. But you still have a copy of the old key in your pocket. That key now points to an empty, decommissioned parking spot. If you try to use that key, who knows what'll happen? It could lead to weird behavior, or it could just crash your entire program. This happens all the time when you have 2 pointers pointing to the same piece of memory. You use delete with the first pointer, which correctly frees the memory. That's good, but the second pointer has no idea that happened. It's still holding the address to that now invalid memory. It's just dangling there, and it's incredibly dangerous. This is exactly why step 5 of our life cycle, setting your pointers to null after you delete them, is so important. So look, if you only remember one thing from all of this, let it be this quote. Just burn it into your mind. Every new must have a matching delete. That's it. That's the golden rule of responsible memory management.
This stuff, dynamic memory, this is the key that unlocks truly powerful and efficient programs. Programs that can grow and shrink and adapt to things you can't predict. It really is a programmer's superpower. So the only question left is, what are you going to build with it?